able to use diagrams to explain what a three-dimensional wave is. Apply the properties of two-dimensional waves to three-dimensional waves and solve real-life problems involving water waves. Longitudinal waves and transverse waves on a slinky spring are only models of waves found in the real world. Real-life waves are a little more complex. They spread out from a source in all directions, and as a result, they have width as well as height and length, and so are 3D waves. Water waves are a good example of 3D waves. So we will explore water waves to learn more about the properties of 3D waves. Can you see that by looking at these waves from the side view, they look just like the two-dimensional waves that we studied previously? They have an X and a Y component. But there is an extra dimension to the water wave, which we can only see when we change our view so that we're looking at the wave from above. Notice there isn't just one crest at the point P, but behind P there's a whole series of crests too. This water wave therefore has a Z component as well as an X and a Y component, making it a 3D wave. We can use an arrow to show the direction of the movement of the energy that the wave is carrying. We call this the direction of propagation of the wave. All of the parts of the wave that are in phase with each other form a wave front, which is always at right angles to the direction of propagation of the wave. You can very clearly see a wave front when you look at the waves that form in the ocean. The ripples that you see spreading out in a circle pattern after a stone has been dropped into water are also wave fronts. Let's go to the lab to look at three-dimensional waves in a little more detail. We can create three-dimensional water waves in a ripple tank.
Hi guys, here I have a nifty piece of equipment called a ripple tank. Basically, it is a shallow tank that is filled with water. It has a piece of wood that can bob up and down in the water, creating straight ripples. The motor is used to make the wood vibrate at a set frequency. Watch what happens when I turn the light and the motor on. There is light below the tank that shines through the water. Small ripples form on the surface of the water. Can you see the parallel light and dark sections on the screen? These are images of crests and troughs of the ripples in the water. Because the light is shining from below, the crests appear as the dark regions. Notice that they form straight lines showing the shape of the wave front. Have a look at this model of a water wave like the ripples you've just seen. If we draw a diagram of this wave, viewed from the side, we get this diagram which you've seen before. To draw a diagram of the same wave viewed from above, we draw a series of parallel lines to represent each of the wave fronts. Notice that there are many points along this wave front. The particles at each point along the wave front are moving up and down together. In other words, they are in phase. The same is true for each of the successive wave fronts. So, all the points on all the wave fronts are in phase, and the wavelength can be found by measuring the perpendicular distance between two consecutive wave fronts. So on this diagram, every point on any of the lines is in phase with all the other points, and the wavelength of the wave is the perpendicular distance between any two neighboring lines. I hope you now have a clear picture of a three-dimensional wave and can see that water waves travel in straight lines from the source, just like 2D waves do. If I attach a small spherical ball to the source, I can also create circular waves in the water. Notice these waves also spread out from the source along straight lines. Now let's use the ripple tank to see if 3D waves behave in the same way as 2D waves when they reach a boundary. You should remember that a 2D wave can either be reflected or refracted when it reaches a boundary. If the wave is reflected, it will always obey the law of reflection, which says that the angle of incidence is always equal to the angle of reflection measured from the normal. Refraction takes place when the speed of the wave changes as it enters a new medium. This change of speed will cause the wave to bend if it meets the boundary at an angle of incidence greater than 0 degrees. Let's see if a three-dimensional wave can also be reflected or refracted at a boundary. Have a look at what happens when a barrier is placed at an angle to the wave front in this tank. Can you see the places where the shadows crisscross each other? This shows that the wave fronts have changed direction after striking the barrier. In other words, the wave has been reflected. Now let's see if a water wave can also be refracted. I'm going to put a piece of Perspex in the ripple tank. The water is shallower above the Perspex and deeper where there is no Perspex. Watch what happens when water waves move from deep water into shallow water. Can you see that the distances between the shadows have decreased? This means that the wavelength has decreased. You should also be able to see that the angle of these shadows has changed, showing that the water waves have bent as a result of moving from deep to shallow water. Now remember, when waves are bent after crossing a boundary, this indicates that there has been a change in speed. Can you work out how the speed of the wave has changed? Remember, the speed of the wave, v, is equal to the frequency, f, times the wavelength, lambda. Here the wavelength decreased. The frequency of the wave remains the same, so the speed must have decreased. Because its speed changed, we can say that the water waves was refracted. In this case, the change in speed is not caused by the change in medium, as the medium is water throughout the tank. The change in speed is caused by increased friction in the shallow water, which causes the wave to slow down. Well, I think that from these experiments, you should have seen that 3D waves can be reflected or refracted at a boundary. Now let's go back to Diasha